Okay, so we're continuing on with this example. Now we're going to see if G and H are independent. So they give us the probability of G, the probability of H, and the probability of G and H. And we're just going to plug it into the formula and see if it works. So the probability of G and H, if they're really truly independent, should equal the probability of G times the probability of H. So let's just check out, see if it works. So we're told that G and H is 0.18. We're told that the probability of G is 0.3. And we're told that the probability of H is 0.6. Does that work out? Yes, it does. So they are independent. Okay. We could have used the conditional probability formula here or here, but we weren't told anything about a conditional probability in these examples, so that's why I used the and formulas to try to show independence. Okay, let's read through this one. In an apartment complex, 30% of the residents watch NBC for their nightly news, and 80% have a computer and can check news on the internet. If the percent who watch NBC and the percent who have a computer to check the news are independent, okay, that's a big deal. Let's kind of highlight that. So we're told that the percent who watch NBC and the percent who have a computer to check news are independent. That means we can use those formulas. Okay, so then it says, what's the probability that a randomly selected person watches NBC or checks news on the internet? Okay, always got to be careful of the wording. This is an or, not a given. It's not an and, it's an or. So probability of NBC or just using the internet. Okay, so when we have an or problem, we add the probabilities up. So we would take the probability of NBC plus the probability of internet. And if there was any overlap, then we would have to subtract off the overlap, which would be the probability of NBC and internet. Okay, well, they told us the probability of NBC was 0.30. They told us the probability of just using the internet was 0.80, but they did not tell us anything about NBC and the internet, people who can watch on their TV and on the internet, on their computer. Okay, well, how do we figure that out? Well, we're told they're independent. So if we go back to our formulas, if you know they're independent, then and is the two probabilities multiplied together. So and should be, let me erase this now, and should be the two probabilities of NBC and the internet multiplied together. So 0.30 times 0.80. Okay, so we would have 0.30 plus 0.80 minus our overlap, which would be 0.24, and our final answer would be 0.86. Again, we could only do this step because we knew they were independent. That's the only reason we could multiply the two together. This is kind of just a side note sort of thing, but it's worth talking about when you're drawing something with replacement and without replacement. So we got to just go through this. So the example, we've got 120 teachers at a lecture, 85 of the teachers are high school, 25 are middle school, and 10 are elementary school teachers. And we're going to randomly select 4 teachers to win a prize. So what's the probability that all 4 teachers are high school teachers if we draw with replacement? So like we draw out a number and we put it right back in. So the probability of getting 4 high school teachers. All right, well, let's think about the first person drawn. There are 85 high school teachers out of a total of 120. So the probability that the first one drawn as a high school teacher would be 85 out of 120. Okay, well, now we put that card back in the hat. So now there's still 120 teachers in there, and drawing out another card, we put the card back in, so there's still 85 high school teachers, numbers or names or whatever, still in the hat. We put it back in. And each draw is independent. Drawing this one does not change the probability of drawing this one because we put them back in the hat. We're going to put it back in the hat again. So now when we draw it the third time, there's still 85 high school teachers out of a total of 120. And then the fourth time, same thing. So when you multiply all those together, you get 0.252. Another way that a person could have written this would be 85 out of 120 to the fourth. That would also have worked. Okay, but now this time we're not going to replace. Okay, so the first time we draw, we have an 85 out of 120 chance of being chosen. But now that card is out. So now there's only 84 high school teachers left, and there's only 119 cards in the hat. And now the third time there's only 83 high school teachers and 118 total left. And we're assuming this is a high school teacher, this is a high school teacher, this is a high school teacher. So that means there's only 82 high school teachers left, and there's only 117 total cards left in the hat. Multiply all that together, we get 0.246. Okay, I want to go back to a problem we've already done. Let's see, back to, yes, this problem. The New York Times and the USA Today. And I just want to ask, are these independent? So are these two events independent? USA Today and New York Times. So if you're ever asked, are they independent, you go to your formulas. Here's our formulas that we could choose from. So if we have any information about and, we can see if when you multiply them together, if it really does equal. Or we could use these ones again. So remember, if they're truly independent, B happening should have no effect. So the probability of A given B would just be the probability of A. Same thing here. The probability of B given A has no effect, so it's the same as probability of B. Now let's go back to that problem. So do you see how we have a conditional probability? So let's check. Is this conditional probability New York Times given USA Today? Is that the same thing as just the probability of New York Times? Like if USA Today has no effect on the probability of New York Times, then they would be independent. So let's check. Well, we found the probability of New York Times given USA Today was 0.125, and the probability of New York Times was 0.25. Oh, they're not equal, so they're not independent. Okay, and then the last thing I want to go back to is this idea. Is it possible for two events to be independent and mutually exclusive? Okay, think about those for a second. Okay, so here's an example of mutually exclusive, right? In mutually exclusive, they cannot happen at the same time. So if one happens, the other one cannot. So if A happens, B cannot. Okay, now each of these had their own probabilities at the time, right? But once A occurs, now the probability of B happening goes to 0. So it changed B's probability. Okay, maybe let me write this slightly differently, and I'll just repeat myself one more time so you can kind of hear what I'm saying. Okay, each of these alone has a probability. Okay, probability of A, probability of B. Mutually exclusive means they can never happen at the same time, and if one happens, then the other one cannot. Independent means if one happens, it has no effect on the other. Okay, but if they're mutually exclusive, they do have an effect on one another. Because if A happens, then there's no way that B can happen, so it changes B's probability to 0. And the key word is that it changes. So they cannot be independent because A happening changes B's probability. That's not independent then. Okay, so